So, welcome to IISER Pune, and I hope all of you are comfortable and ready to attend lectures, because this is more of a thing like we all are attending some classes, and I hope we really are like students and gain something, because we have very good experts of this subject, and Abhijit and I really wanted this activity for past, we've been talking about it for past 1 year that we should have, and we should really organize speakers. So, the credit goes to Abhijit that he got hold of experts, and they're very kind to really agree to come. So, we welcome everyone, and now I request our department chair Amit Hogadi to formally welcome you all, and then we can start the session.
So it's a pleasure to welcome you all. I can see a lot of familiar faces, but it's also good to see many people who have come here probably for the first time. Special thanks to Rama, Tejas and Abhijit for the effort of organizing this. And I wish you a fruitful, how many days? 3 days? 5 days, okay. 5 days of conference. So thank you all for participating.
The first speaker is Ilya Kaufman from City University of New York, and he's going to tell us about an introduction to the colored Jones polynomial.
Thank you. Can everybody hear me? So I just wanted to explain this is a workshop on the volume conjecture. The volume conjecture has two pieces, two parts to it. There is a quantum part, a diagrammatic part, and there's a geometric part. So what we've decided to do is I will give 3 talks to kind of get everybody up to speed on the diagrammatic part, and Abhijit will give 3 talks to get everybody up to speed on the geometric part. And then Hitoshi will speak about Hitoshi Murakami will speak about how these two go together and state and explain the volume conjecture. That's kind of the idea. So these 3 talks of ours will help you understand this conjecture that's been of interest now for 20 years, I think is a fair statement, roughly. So, okay, so let me start. I will give you a little bit of an introduction and then explain my plan for these 3 talks, okay? So let me start with the beginning of all of this is Jones. This is Vaughan Jones in 1984. Discovered a polynomial invariant, which is now called the Jones polynomial, which lives in this a Laurent polynomial in T. And this Jones polynomial was discovered by studying representations of the braid group. So what Jones did is he discovered a whole infinite family of representations of the braid group into finite dimensional Hecke algebras parametrized by a complex parameter T. So I don't know your background, so you need to ask me questions. If you just sit there very quietly, I'm not going to know where to stop. If I'm saying something you don't understand, does everybody understand what a representation is? So a representation, right, is a homomorphism that respects the relations in this group, and this I don't expect you to know. So these are some finite dimensional algebras. This is n is the dimension. This is some parameter, and this is a relatively complicated piece of work. Just to give you an idea, this was in 1984. The only braid representation, the only finite dimension, the only braid representation of any kind that was non-trivial was the Burau representation, which was discovered 60 years earlier. So what Jones did is Jones found a whole world of representations of the braid group. He showed that every representation of the symmetric group, I don't know if you've studied representations of the symmetric group, SN. It's a typical kind of the first thing you study in a representation theory class. What he showed is that every representation of the symmetric group lifts to a representation of the braid group. So suddenly, all of them lift. And so this was really an amazing discovery. And so a lot of this comes from this representation theory. Okay, so what has happened since then is the ideas of the representation theory have kind of been put a little bit to the side. And let me explain this. So the Jones polynomial itself, vk of t, satisfies several different relations. Okay? So in particular, it satisfies the oriented skein relation. And I'll show you an unoriented skein relation, but it looks like this, right? So if I do T inverse V, so if I take a little part of a diagram that looks like this, minus TV, a little part of the diagram that looks like this. So this is a positive crossing, this is a negative crossing. I'm following right-hand rule here, right? So this will typically be, this little part of the diagram will sometimes be denoted by L plus and L minus. Right? So it's like a little piece of the diagram that just changes. And the relation is it's root t minus 1 over root t times v of a little part like this. So this is L0. So L plus, L minus, and L0. And so if you study knot theory, if you know knot theory, this is very reminiscent of the Conway relation for the Alexander polynomial. This is called the Alexander-Conway polynomial now. So just for comparison, kind of like off to the side here, so this is VL plus minus L minus is equal to Z L0. This is the Alexander-Conway polynomial. So this is nabla. This is nabla, and it satisfies a similar relationship. So of course, when Jones came up with this oriented relation, the knot theorists all knew about this one, for more than, for years earlier. And so immediately there was an effort to find a common polynomial that satisfies both of those kinds of relations. And that is the Home Fly polynomial. So the Home Fly polynomial is the natural generalization for which it's a two-variable polynomial, which can be specialized on the one hand to be the Jones and on the other hand to be the Alexander-Conway polynomial. And there were several other two-variable polynomials, like the Kaufman two-variable polynomial. That's a different kind of generalization. But so the point is that that's a different kind of thing. You see, we've left representation theory, and we're now working with different kinds of relations like this, diagrammatic types of relations. So the importance of the Jones polynomial, the first thing that Vaughan Jones figured out is that if you look at the right trefoil, right, this is t plus t cubed minus t to the fourth. And if you do the other trefoil, right, of t, this is minus t to the minus fourth plus t to the minus third plus t to the minus first. So this is the first, what he had discovered was the first polynomial invariant that could distinguish the two trefoils. Right? So one trefoil is distinct from its mirror image. So this was, again, known decades earlier, this fact, but this is the easiest way to prove it. Okay?
V is the Jones polynomial.
Yes, V stands for Vaughan, the first letter of his name. Okay? So
Like it's the Jones polynomial of whatever
yes.
grade or not.
Yes. So yeah, it depends. This is like a typical notation where you write the knot, like in the corner a little bit. Yes. Okay. So this is a very strange invariant in topology. If you take a topology course, typically topological invariants are straightforward to define and then very hard to compute. Right? Good luck computing a spectral sequence of some interesting space. Right? It's hard. So, but what happens is here, the invariant is relatively easy to compute for any particular example. You just do it, like a high school student could do it if you show them the rules. I'll show you an algorithm. But understanding this invariant has proven to be very difficult. So this is from 1984. Let me show you two problems that are still wide open that indicate how poorly understood this invariant is. So these are open problems. The first open problem is if I say that the Jones polynomial is trivial, if I have a knot whose Jones polynomial is trivial, is this the unknot? Wide open. Okay? Recently, it's been proved for Cavanaugh homology that Cavanaugh homology detects the unknot, but for the Jones polynomial, that is still open. Okay? The second question is, given any geometric, topological data for the knot complement. So for example, if I give you the fundamental group of the knot complement, can I write below this line, or is that very bad? Well, let me say. So given any such data, here is the question. What is the Jones polynomial? So in other words, if I tell you anything you want to know about the knot complement, any geometric invariant, any topological invariant, any algorithmic data, whatever you want about the knot complement, tell me the Jones polynomial for the corresponding knot. No idea. So it's completely unconnected to the geometry and the topology of the knot complement as of currently. In contrast, the Alexander polynomial, the Alexander polynomial was discovered by Alexander in the late 1920s. Within a decade, Seifert answered both of these questions. So he found a construction to produce knots and links with trivial Alexander polynomial, and it was completely understood in terms of the knot complement. That's, in terms of the Seifert surfaces and so on. I'm just giving a comparison to the other famous knot polynomial. And so this kind of gives you a sense. This is why a knot theorist would say the Alexander polynomial is well understood, but the Jones polynomial is not well understood. Okay. All right. So I'm trying to give you two kinds of information here. One is this invariant is important, and two, this invariant is mysterious. Okay. That's kind of the take-home message here. All right. So from the Jones polynomial, within the next period of time, I don't know, 10, 15 years, there were many other invariants, so many sort of families of invariants. Because the Jones polynomial has been at the kind of the center of knot theory for a long time, I could give you many examples of this. For example, the specializations of the Home Fly and the Home Fly PT, Kaufman, and two variable specializations. These words are a little bit mysterious if you haven't seen this, but basically from two variable polynomials you can construct infinite families of one variable polynomials. There are replacements if you replace t with e to the x, for example, and take a Taylor series expansion, you get what are called Vasiliev invariants. Vasiliev or finite type invariants. There are lots of ways to construct other invariants from the Jones polynomial that people have figured out what to do. The most famous recent one is Cavanaugh homology. Gives you a whole host of other invariants. This is a bigraded complex. It's not your usual homology. So the Euler characteristic of this homology theory is a polynomial. You can think of every coefficient as being an Euler characteristic of a column of a complex. So you have columns of complexes where every Jones coefficient is an Euler characteristic. Another connection is due to Tut. So the Tut polynomial equals the Jones polynomial if k is alternating. So the connection here is using spanning trees. Okay, so there are many, many ways that this polynomial, the Jones polynomial, has played an active, important role in knot theory. This gives you a spanning tree expansion. This is a categorification. That's kind of the magic word here. If you haven't seen this, it will mean nothing to you. But it's basically, OK, let's move on. And so these kinds of things have led to many, many directions. I have 1 hour to tell you something about the Jones polynomial. So I'm not going to say anything about any of this, except that there are these families of invariants that basically come from here, right? So these types of invariants are what are called quantum invariants. So these kinds of quantum invariants are so called because they're organized. The invariants themselves are organized using representations of quantum groups. So they come from quantum groups. And so my goal is to basically, in this lecture, tell you more about the Jones polynomial. And then in lecture 2, so let me do it like this. So lecture 1 is about the Jones polynomial. In lecture 2, what I want to do is I want to spend a little bit more time on the representation theory and talk about the Jones-Wenzel idempotent. So this falls into the world of skein theory. So I'm going to talk, lecture 2 is going to be skein theory. And then lecture 3 will be about these quantum invariants and quantum groups. So in all 3 of these, I'm going to scratch the surface and then leave you very eager to read more. That's my goal. OK? OK. So that's my plan in these 3 talks. OK. Any questions? So this is kind of an overview. Any kinds of questions? There's a discussion section at the end of the day. That's our plan. And if someone wants to discuss some of these other directions, I think that would be fun. So we have an expert on Cavanaugh homology here. Where's my? Yeah. There you're sitting very quietly. We have an expert on Cavanaugh homology, so we can have that kind of a session or some other kind of thing. Sure. No. No. Is that somehow better? OK. All right. OK. So now we're going to do it much. I want to talk a little bit about the Kaufman bracket polynomial, which I'm assuming some of you have seen before. So I want to speak a little bit. This is a rather more elementary approach to the Jones polynomial, and it will set up what we need to do for the skein theory part. So this is work by Kaufman. Kaufman bracket polynomial. And it was discovered around 1987, a few years after the Jones polynomial was discovered. And what this is this is an axiomatic version of the polynomial. So Right, so I'm going to show you two approaches. So one is axiomatic and one is state sum. Those are kind of the two different ways to think about this. So here's how we're going to start. So let D is going to be an unoriented diagram of a link. Okay. And we're going to see this distinction all throughout in all three lectures. You have a choice when you're given a link, a knot or a link diagram. And your choice is fundamentally to provide this diagram with an orientation, in which case, if you have an orientation, the whole theory goes through without a need of a choice of framing. Or you can be unoriented, but then the framing matters. You have to worry about the framing. What is framing? Framing is, well, if I draw a knot like this, the framing is usually given to you by the blackboard itself. So what we talk about is we talk about a push-off. So there's a choice of longitude that can be made on the knot itself. And whenever I draw a diagram on a blackboard, there's something called the blackboard framing. The blackboard framing is a choice of longitude in the knot complement that is just pushed off in the blackboard, just according to the diagram itself. So for example, had I put in a little kink here, that would affect the framing. Okay? That's a different framing. So there is a choice to be made about a longitude on the knot complement. These invariants, these types of invariants, come to you, the input that they take is either an unoriented diagram with a choice of framing or a diagram with a choice of orientation. And we'll see this dichotomy in all throughout. So we have to worry about. This is something to worry about. Okay? So we start with an unoriented diagram. Okay? And we're going to resolve the crossings. This is Kauffman's insight, is that you can label these regions of the diagram by A's or B's. And the way that you get your A's or B's is if the A region is the one that's swept out counterclockwise. Right? If the region that's swept out counterclockwise is the A region. So then you can resolve. So people have used the word splice or smooth. I think smoothing is now more common. So you can resolve this crossing into. I'm sorry? Yes, of course. Thank you. B and A. Thank you. Okay? So you can resolve this crossing by joining up the A regions or joining up the B regions. And sometimes you put little markers there. So people call those little markers, just in case you need to remember which it was. So you can smooth your diagram or splice your diagram, whichever verb you like, into these A's or B's regions. So then what we get is we get the bracket, which lives in the Laurent polynomial in A, okay, by these three axioms. So the first axiom is that this is A times this bracket plus A inverse times this one. The second axiom is if I have an unknotted component and I have some other diagram, then that comes out with a coefficient called delta, where delta is minus a squared minus a to the minus second. And the third axiom is some kind of normalization. It depends on, this is a choice. It depends on different people make different choices, but a typical normalization is to set it equal to 1 on the unknot. So this is an axiomatic approach, and using these three axioms, like I said, a high school student could compute.
There's an unlinked circle.
Yes, an unknot. So these three rules are completely sufficient. Let me give you just a very quick. Let me give you a very quick example here of how this would work. So if I take a single unknot with a kink. So this is an unknot with one kink. This is the simplest thing you could possibly do. Notice this is positive. So for a knot, so right. So anyway, so this is a positive crossing, right? Because if I orient here, right, you see right-hand rule tells me that's a plus. So then what do I get here? This is A times this resolution. Here, let me do it on the board so you can see it. This is one of the advantages of chalk. So you can see that the A smoothing, if I smooth here, you smooth like this, right? Right? So that's A plus A inverse times smooth the other way. OK? So that's A plus A inverse. And so what we see then is we see this is A delta of this unknot plus A inverse of this unknot. And when I combine all this together, this just becomes A times this minus A squared minus A to the minus second plus A inverse times this unknot. And what do we get? This is 1, and then the things that's left is minus A cubed. So notice it is not a knot invariant. We do not get a knot invariant because that's an unknot, and we didn't get 1. This is the framing issue. So this is what we need to adjust for the framing. Because if you do it for the other type of crossing, so if you do this kind of gadget, what you're going to get is minus A to the minus third. So this is where we need to do a framing adjustment. And it is this idea of a framing adjustment to get a knot invariant that persists. We're going to see this in all 3 lectures. It's this idea of that you have to adjust by framing. So no, framing is framing, and orientation is orientation. If you have a knot, so good observation. If you have a knot, only for a knot, not a link. If you have a knot, the framing is how do I say this? The orientation gives you a sign on the crossing. Okay, so the orientation gives you a sign on the crossing. If you have a link, different choices of orientation could give you different signs on the crossings. So look, if I reverse if I reverse this, right? So now I'm going the other way, right? If I reverse it, I still have a positive crossing by right-hand rule. But if I had a link, then I could have different choices here that will give me different signs on those crossings. So there are 3 different kinds of signs. There are signs that come from framing, right? There are signs that come from the choices of orientation, right? This is an issue. So the right way to approach the Kaufman bracket is forget about orientations, right? No orientations, and just worry about framing. Okay? So in other words, this gadget is different from, right, the one that's just the usual hop flank. These are not equal. Right? Because this has a different framing. Okay? All right. So what is the adjustment that we make? So the adjustment that we make is the following. Okay? We observe yes. So it's a choice of longitude. If you have a diagram that's presented to you, it has what's called a Blackboard framing, which is the one that's commonly used. There are 2 commonly used framings. One is the Blackboard framing, and one is called the zero framing. The zero framing is, so like for example, this has 3 crossings, all positive, right? So this is, this is 3 positive crossings. So if I want the zero framing, I need to put in 3 negative kinks. right? I put in three little negative kinks. Are those negative? Yes, those are negative. So 3 positive crossings, 3 negative crossings gives me a 0 framed diagram. So people typically use either the 0 framing or the Blackboard framing.
This framing is same as the linking number of the longitude.
It is a linking number of the push-off in a certain direction. So it is in the Blackboard framing is the one for which the linking number is the one from the writhe of the diagram. Let me tell you what the writhe is. Okay, it's exactly right. So I'm sorry to confuse. I understand this is a relatively technical point, but we're going to need this. This is an important technical point. Okay, so there's something called the writhe. Okay, this is a notion that goes back more than 100 years to Tate. And the idea is the following, that the orientation gives you a sign, right? So this writhe here would be a positive writhe, right? So the idea is I give you some diagram with an orientation, add up all the signs. That's the writhe. And the observation is that the writhe of this fellow is equal to 1 plus the writhe of this fellow, right? You just undo the kink. And that is, and similarly, right? So we have, right, we saw before that that computation over there basically shows you that if I compute the Kaufman bracket of this guy, this is minus a to the third times the unoriented thing without the kink, right? So the natural adjustment to be made here is the following adjustment. So we define, it turns out to be the Jones polynomial in the variable a, so I'm going to cheat a little bit, but it's a link invariant, which is defined to be minus a to the minus third. Notice this extra little minus there, times the writhe of the diagram d times the bracket of d. So this turns out to be the Jones polynomial with a change of variables. T is a to the minus fourth. So it just looks like a trick, but it's a trick that works. So the idea is knowing the writhe of a diagram is enough information to get a link invariant, because this is the exact adjustment you need. OK, so we recover the Jones polynomial. And so, for example, so here's like a small homework is to compute this. So here's a little homework. Make sure you can compute the bracket of a trefoil. So this in A's is going to be a to the minus 7 minus a to the minus 3 minus a to the fifth. And then you can see that the writhe here is a plus 3. And so you get that together, these two pieces of information gives you that the Jones polynomial in A is minus a to the minus 16 plus a to the minus 12 plus a to the minus fourth. And then when you do this variable change, you'll get back the Jones polynomial for the trefoil. OK, so vk of t, as before, is minus t to the fourth plus t to the third plus t. OK? I did. This is the writhe, and then this is the bracket. This is the writhe. That's the adjustment with the writhe. Did I make a mistake? This should be OK. No, it should be OK. All right. All right, so let me say something non-trivial here, and that is that if k star is the mirror image of k, that's a notation. So I should say let k star be the mirror image of k. Then what we see then is vk star of t is vk of t inverse. Because if you take the mirror image, then in the Kaufman bracket, A's go to A inverses. The writhes all become opposite. And what happens is you can just replace the T with the T inverse. And so, right? So is that clear? So therefore, if the Jones polynomial is not palindromic, is that a word you guys know? Palindrome, right? So if you read it one way and you read it the other way, it's the same. So a polynomial is palindromic as if you read it one way and read it the other way, it's the same. Replace T with T inverse. How's that? Okay. So if the polynomial is not palindromic, then K is not equal to its mirror image. There's no guarantee if it is palindromic, but if it's not, no chance for the not to be equivalent to its mirror image. Okay? If you compute it for the figure 8 knot, you'll see it is palindromic. The figure 8 knot is equivalent to its mirror image. The figure 8 knot is this guy. Okay, so this knot happens to be equivalent to its mirror image, and its Jones polynomial, therefore, is palindromic. Okay, symmetric in T and T inverse. Okay, and for the trefoils, it's not. Okay, so this is the axiomatic approach to the Jones polynomial using the Kaufman bracket. Let's see the other approach to the Jones polynomial using the Kaufman bracket, and that's called the state sum approach. The converse is not true. So let's look at the other approach, which is a state sum. Okay. So this is again due to Kauffman. And the idea is the following. Suppose, so if D has C crossings, okay, then you can look at all possible smoothings. So A and B smoothings. And what you get is 2 to the C states. So what's a state? Okay. So let's do this again for the trefoil. Someone once joked that all of diagrammatic knot theory is the theory of the trefoil, and all of geometric knot theory is the theory of the figure 8 knot. So if you just know those 2 knots, that's good enough. You don't need to know any others. Okay? So the trefoil, the reason you can see the issue here is this is exponential. So all of the computational parts of the Jones polynomial, everything is very easy when I give you a 3-crossing knot. I'm going to get 8 states. But this is an exponential problem. Okay? And this actually has a lot to do with quantum computers. Right? I'm supposed to say quantum computers, sprinkle that in my talk to make it sound important. But the idea is this is true. So Microsoft hired, mathematicians who've been studying the Jones polynomial. I'm not kidding. Because this is a computational problem, and computing the Jones polynomial at various roots of unity is known to be an NP-complete problem. So if you can solve this exponential problem in polynomial time, you can solve any exponential problem, including the RSA algorithm, in polynomial time. So this is a really important gadget that people at Microsoft understand computations of the Jones polynomial at certain roots of unity very, very well. So that's quite an interesting sort of fact. But anyway, there's a whole computational piece to this. But keep in mind, everything I'm telling you is of exponential complexity in the crossing number. Okay, and then when we talk about the quantum stuff, that's not clear that that's exponential complexity. So there's a lot of people who are trying to bring the physics into this problem. Okay? All right. So, okay, let's get back to the simple stuff. This is a 3-crossing diagram. And if I want to do an A smoothing at this crossing, it's easier for me on the blackboard to just redraw it, right? So the A smoothing is going to be this smoothing. Right? You want to be taking your notes in pencil at this point. So this is an A smoothing here. So now I'm going to do another smoothing here. Let's do a smoothing here. And so I'm going to get, we smoothed it this way, we smoothed it this way, we smoothed it this way and this way. So here are two A smoothings. And now if I want to do one more, right, I'm going to get this kind of picture. Right, so here are your three, right, the last one. So this is the all A state. Right, so there's a little, if you care about the markers, one here, and one here, right? This is the all A state. So there are 8 of these states. There's 2 to the third, right? There are 2 to the third, which is 8 states for this diagram. Okay? And so what you see is you get, so at every step here, you can do an A or a B smoothing. Then you can do an A or a B smoothing. You can do an A or a B smoothing. Right? And these are your 8 states. Right? So you get this, what's called a skein resolution tree of all. And at the end, you have crossingless diagrams, little crossingless diagrams at the end. And so what's the invariant? The invariant is that the Kaufman bracket can be written as a sum over all of these states S of A to the. So for every state, you did some number of A resolutions and some number of B resolutions. Take that difference. And then at the end, you'll get some loops. So that's going to be this delta value, minus A squared minus A to the minus second, times the number of circles in the state minus 1. All right? So that's the formula for the state sum for the Kaufman bracket. All right. So let me leave it at that. There is a state sum. So what we need to know is we want to generalize this further. Okay? So how does this generalize? The next generalization that we need is something called the Kaufman bracket skein module. Okay? So that's kind of the next step here. And the idea is the following. So now we work in the world of tangles. So let's take a rectangle with some marked points. So here is, let's do, so 3 marked points here and 3 marked points here. All right, and so this is R6. This is a rectangle with 6 marked points. I'm avoiding writing down definitions. I'm kind of defining by example. If you excuse me, this will be much faster. So the idea is to draw some tangle here. I'm just going to draw some tangle here. Let me see here. Okay. Right, so here's some tangle in there. And I can do my whole Kaufman bracket machine inside the rectangle, fixing the points on the boundary. So this is the Kaufman bracket skein module of this rectangle with fixed points on the boundary. Okay? So in general, I've got, let's do mu of R is going to be the free ZAA inverse module. Right? This is some ring. You get some module with these coefficients, right? Generated by these n tangles. So this is typically called a 3 tangle, right? 3 on top, 3 on the bottom. It's called a 3 tangle. So it's generated by n tangles in R, R to n, up to equivalence. And by that I mean tangle equivalence. right? So you can do some isotopy of tangles here. So up to tangle equivalence, you get a free module doing the Kaufman bracket inside the rectangle. This has been generalized in many directions. So for example, let me just give you an example here of a generalization. E.g., you could do this on a surface. All right, let's mark. I pick 2 points, mark it on a surface, and go around and do something. Okay, so here you could do the Kaufman bracket skein module of diagrams on a surface with some number of points on the boundary.
So instead of rectangle,
Yeah, you could do this. I'm only going to talk about rectangles. I need it for what we're going to do next. So I'm just going to say there's a whole bunch of stuff you can do with Kaufman bracket skein modules. This is for, yeah, but it's on a surface. There's genus. So this is some other thing going on here. But you could do this in any 3 manifold. Here, no. Like I said, this is an extremely general setup. I would like to talk about rectangles. Okay? All right. All right. So this is the free module. So let's define the Kaufman bracket skein module. The Kaufman bracket skein module, S of R, is this free one quotiented out by the Kaufman bracket relations, right? The usual Kaufman bracket relations, which are equal to A inverse plus A inverse this guy, and the usual one, D with an unknot, is equal to delta D, where delta is minus A squared minus A minus second. So what does that mean? I'm being casual here, but I want you to know what I'm talking about. There is a 2-sided ideal inside this free module generated by the difference of this guy minus that guy. So take the ideal generated by these relations and quotient it out by this ideal. Okay? Technical stuff, sweep it under the rug. These are the relations. Okay? All right. Let's look at some examples.
This tangle equivalence is just like not equivalence fixing the endpoints.
Yes, correct. Okay.
so it's an independent thing. It's not dependent on which tangle you're taking or not.
No, the tangle affects the values of the Kaufman bracket relations. I'll show you. I mean, this is the.
So it differs by tangle by tangle. If you take this S of R is what? It is tangle dependent?
No. S of R depends on the space. This is like homology. This is like the homology of a space. So this is the Kaufman bracket skein module of a space.
Okay.
And to some degree, it determines the space, or the space. Well, certainly the space determines the Kaufman bracket skein module, but there's some obstruction that it gives
So
you.
right now we are just talking about rectangle.
Yes, I want to
S of
talk
R.
about the rectangle with some fixed points on the boundary. But you could compute the Kaufman bracket skein module of S2 cross S1. Right? You could compute the Kaufman bracket skein module of a 3-manifold with boundary with some marked points on the boundary. Okay. The 6 is the number of points, the marked points. Those points are going to stay fixed throughout the isotopy. So the tangle equivalence respects those points. They cannot move. You can do whatever you like. Imagine them as strings, and those are nails. Those are nailed in. They can't move.
If you change n, it will change?
Yes. R8 would have 4 and 4, would be for 4 tangle.
I see.
Okay? All right. So we need this. The reason I'm doing this is because we need this. Okay? So, but all right. So here is the idea here. So here are some basic examples. Okay. So example 0 is the one that you've already seen. The Kaufman bracket skein module of the plane of R2 is just one-dimensional, right, with basis the empty link. right? So in other words, you're just going to do the Kaufman bracket, and that sits inside here, you know, adjoined to this guy. I don't know. Something like, maybe I shouldn't write that. I don't know. Just sits inside here. I don't want to confuse the issue. But this is, we've already seen this example. So let's do the more interesting examples. S of R4. Okay. This is a rectangle with 4 marked points. Okay. And what I'm going to do is I'm going to now start writing circles because it's easier.
Is the upper one R suffix to?
This is the plane, just the plane, the Euclidean plane.
Okay.
So links in the plane. So this is a free module, right? With basis, right? So can you see if you do all Kaufman bracket resolutions, if you get rid of all the crossings, what could you possibly get? Well, your basis could be either tangles that look like this or tangles that look like this. That's your basis. Okay. If I do S of R6, this is going to be have a 5-dimensional basis. And the basis is going to look like this. Okay. Okay. So the same 6 points are fixed on the boundary. Okay.
So should it be obvious that the basis is always things with no crossing?
Yes, because every crossing you resolve with the A and A inverse business. All crossings get resolved. And so the basis is what's left, like the crossingless diagrams. So you'll notice if you continue this, S of R2n has dimension, anybody know? The Catalan numbers, yes. I need non-experts to answer. 2n, choose n, has dimension equal to this, which is the nth Catalan number. So they start like this. So you'll notice this is 1, 2. Next one is, let's see, 5, 14, 42, and so on. Right, so this is 1, 2, 5, and so on. Okay? All right. Now, let's see this for, yeah.
So we are considering only tangles with the same number of points fixed above.
Yes, yes, yes. So let's see this from the point of view of an algebra structure. Okay. So we have algebra generators. So this is an issue about we are going to deal with an algebra, we're going to deal with a vector space, with a corresponding vector space. You have to be careful. When I talk about dimension, I'm talking about a corresponding vector space. But the algebra generators are slightly different, so just be careful. So the algebra generators are the following. So these are, this will be called 1. Then we've got E1. Then we've got E2, and so on, up to, right, En. Right. These are the algebra generators. And so the basis elements look like this. So like if I take E1 times E2, then that will look like this. So this is E1, and then I multiply by E2. You see what's happening here? This is going to look like a little crossingless diagram. So E1 times E2 is this little crossingless diagram. Thank you. Thank you. All right. So these are the generators, and so you have relations like this. So this is E1, E2. E2, E1 looks like this. So if I connect this up, it looks like this. All right. Different crossingless diagram. And so there are relations in the algebra for example, if I do E1 squared, E1 times E1, I'm going to get a relation that looks like this. So that's equal to delta E1, right? So I get a relation like that.
So these are relations you're saying in SR.
Yes, that's the point. That's why I'm doing this. I want to explain this. So we're recovering these elements here as basis elements for a corresponding algebra with relations.
So this is a different algebra that we created.
Yeah, well, you can see this is the algebra of elements in the skein module. These are elements in SR2n.
So SR2n.
Yeah, so these are elements. Yeah, I guess I
so
should have been.
It was vector space. Now it has an algebra structure.
Yeah, it's a module.
And whose generators are.
That's right. So it's a module. There's an underlying algebra, and the algebra relations.
Multiplication is just because
Yes.
you
Yes.
can just concatenation.
Correct.
Is the tangent.
And all of these crossingless diagrams, all of these elements are coming out as an underlying vector space.
The natural multiplication is there. It's just that he's writing down the.
Okay.
relation.
So let me make this clear now. So here is the idea then. Okay. One second. Let me just put it on the board. Put all this together. Right now, I've just thrown some examples up. Give me 1 second. Okay. So the idea is we are going to turn SR2n, okay, into an algebra. So it's a module. It's getting upgraded. Okay. So we're going to turn it into an algebra with this product. Okay, so the product is exactly this concatenation. All right, so let's do, for example, here I'll just do. Right, so I take one of my crossingless diagrams, multiply. So here's what multiplication looks like. I don't know, should I do it horizontally or vertically? Let me do it. I don't know. Vertically is more intuitive, I guess. But in paper, if I take notes, I do everything horizontally. Right, I'm just doing some example here, right? So I'm multiplying. I take this guy, and this is the multiplication. The multiplication is the concatenation, right? Right, the concatenation is going to be right like this. Okay, that's the product. All right, so we identify, right, so to be precise, we identify the n marked points, okay, and then and use isotopy. Okay, so with this product, SR2n, this algebra that we now have created, has a name. It is called TLN, the nth temporally Lieb algebra. Okay, and this is famous. This is from the 1970s, late 60s, early 70s. The Temperley and Lieb were physicists studying statistical mechanics. So this came out of a statistical mechanics model, and this is the algebra that you get. So the generators are 1 E1 up to En minus 1, and the relations are EI. Let me do the relations where I have a little bit more space here. The relations are EI plus 1 EI is equal to EI. EI squared is equal to delta EI. And EI EJ is equal to EJ EI if they're far enough apart, if I minus j is bigger than 1. These are the three relations. This is called far commutativity. If the indices are far enough apart, they commute. If the indices are adjacent, this should remind you of a relation in the braid group, right? This is exactly what happened to Vaughan Jones. He saw this, and someone suggested to him the very famous, actually, example. Vaughan Jones was giving a talk about his algebras that he had discovered, and a graduate student raised his hand and said, "Isn't this very similar to braid relations?" Very famous example of a graduate student motivating a very big research area. So ask questions, right? So, and then EI squared is this delta EI that we saw earlier. OK, so typically what happens is there's a parameter here, right? There's this A that keeps hanging around. You can think of that A as a parameter. So what we typically think of is A hangs around. It's a non-zero complex number, right? And also, in addition, we require that A to the fourth not be 1. So it's not a fourth root of unity. When A is a fourth root of unity, the representation theory is different. There is representation theory. It's interesting, but it's not what we care about today. So this temporally Lieb algebra is one of the kinds of algebras that Jones came up with. And he found these representations of the braid group. And this is the one I want to focus on. Okay? It is the right one to talk about. I'm going to run out of time at some point. I'm just going to stop when I run out. If you could just stop me at some. Can you like raise your hand or something? Okay. Okay. So here's the connection to the representation theory that Vaughan Jones had. Okay. So now notice what we're doing is I'm circling back. So we had the whole representation theory that was used to discover the polynomial. Kaufman found this diagrammatic state sum, axiomatic approach. Let's use it now to return and recover the representation theory. So if we set tau, do I need tau? Yeah, so, right. I'm going to skip. I'm going to try to go a little bit. Do I need this? OK, so here is the idea. So we can look at Jones's algebra, right? Can be thought of as this TLN. OK, this is one example. This is the like I said, he had a very large theory. He had a big idea of using all Hecke algebras. If you know any of this complicated algebra stuff, the temporally Lieb algebra is one kind of Hecke algebra, these von Neumann operators and projectors. And so the TLN is the correct one of the many that he did that corresponds to the Jones polynomial. So let's focus on that one. Okay? So the idea is the following. We can construct a representation of the braid group Bn into these Laurent, well, this is not a representation, it's a map, right? So the representation is into TLN, and then we're going to do one more map. So I should not rush so much. Let me stop. We find a representation. This is rho. And then there's an additional element here called a trace. This is rho, and there's a trace into here. Okay? So this is not only a representation, it is a representation that admits a trace. That trace will correspond to the normalization that we saw for the writhe. So this is an extra structure on this algebra. Okay? So the way this works is like this. So we take a braid. So this is some braid element sigma I in your braid group. Right, so this is the ith strand and the I plus first strand. And we send it to, not surprisingly, this is I and I plus 1. We send it to A times the identity braid. Do you see how I'm doing the smoothing? This is the Kaufman bracket smoothing. Plus A inverse times a non-braid element, right? You can see that's no longer a braid. I'm doing something very, very against the rules in the braid group, but I'm not in the braid group. I'm in TLN. So this is A plus A inverse times EI. I'm sorry? Yes, maybe there's an extra line. Oh, what am I doing wrong?
Oh, it doesn't matter. It's like
Okay.
he has plenty.
All right, I've got it. Okay. So the element sigma I is going to A plus A inverse EI. That's the map. Okay? So now let's quickly check, right? So if I've got, this is my rho. So here are the things to check. Rho sigma I times rho sigma I inverse is equal to 1. So you should check that. So what is sigma inverse, by the way? So where would sigma inverse go? So if I flip the crossing, right, this is going to be A inverse plus A EI. Do you see that? If I flip the crossing, then this strange fellow becomes the EI, right, and this guy becomes the identity element, right? So you should check that when I multiply these, I get 1, right? And check that the braid relations are satisfied. OK. So now, now we have this construction. What do we do with it? We turn to an older theorem in the study of braids due to Markov. Okay. So this is a theorem due to Markov. It's very early. It's, I don't know, 1930s, something like that. But it had a bad proof and was reproved later. It's in Joan Berman's book on braids, links, and mapping class groups. So she's got a whole thing on proving this theorem, which was proved 50 years before that. So I don't know who to give the credit to, but it's universally called Markov's theorem. And here is the theorem. Okay, if I give you a braid beta n in Bn and beta m in Bm. So I give you two braids, one of index n, one of index m, and their closures are the same. They give you the same link, L. So suppose I give you two braids of different braid index whose closures give you the same link. All right? Then the statement is, so if this, then beta n and beta m are related by these moves. Okay, and the moves are, one is equivalence in the braid group in Bn, whatever, let me say braid group. So, right, so there are these braid relations. The equivalence in the braid group corresponds to Reidemeister moves R2 and R3. Everybody familiar with the 3 Reidemeister moves? Yes? 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 If not, please ask. Right? But anyway, the equivalence in the braid group gives you 2 out of the 3 Reidemeister moves already. The second one is a certain issue with braid closure, which is conjugation. Okay, let me explain the conjugation piece of it. Suppose I give you a braid beta, okay, and I give you any other braid alpha here and alpha inverse here. Then if I take the closure, then you can see the alpha and the alpha inverse will cancel. So whatever is going on, this should be an invariant. This should be something that depends only on the conjugacy class of beta. So up to conjugation, that's one thing. And the third piece is the Markov move. And this is the statement that Bn can be exchanged with Bn plus or minus 1 generator in the next braid group. So this is what this picture looks like. This picture looks like this. So you take a braid beta, okay, and you add 1 more generator. And now let's take the closure. All right, and you can see that's Reidemeister move 1. That's your R1. Okay, so the Markov theorem is that 2 braids give you the same closure if and only if they're related by 3 operations: equivalence in each braid group, conjugation in the braid group, and the Markov move. You can see why it's called a trace, because the trace is an invariant of conjugacy. So first of all, you need a representation. That's what Jones found. You need a trace. You need a representation into a space that admits a conjugacy invariant. That's step 2. And step 3 is you need to show invariance under the Markov move. And that's a theorem. Okay? So right, so let me just write down what I just said. Okay? So all right, I'll just stop right here. So I'm just going to write down what I just said. So you need a representation, rho, from Bn into TLN. Okay. And then you need a trace, TR, from TLN into ZA plus or minus 1. All right. And so using these 2 pieces, what you get is you get beta going to this row of beta, going to the trace of row of beta. And that element is exactly minus a to the minus 3 times the writhe of the closure of beta times the Kaufman bracket of the closure of beta. All right? And up to a change of variables, t equals a to the minus 4th, that is the Jones polynomial as originally constructed by Jones. So this is the full circle now. So we started with the representation theory. We understood the Kaufman bracket interpretation combinatorially, axiomatically, and as a state sum. Then we constructed the Kaufman bracket skein module, understood that Kaufman brackets, kind of promoted that skein module to an algebra with an algebra operation. And then using that algebra, we recovered the Jones representation as a braid representation. So that's the view of the Jones polynomial, both from the diagrammatic part and the representation theoretic part. What we're going to see in the next 2 lectures, the thing that I want to do is this is going to be a little bit more complicated. What we need to do is to promote all of this to the color Jones polynomial. So this is the one variable Jones polynomial. And so what we want to try to do is understand how these ideas can be kind of lifted to the color Jones polynomial. So in the next lecture, I'll do this from the point of view of skein theory. And in the third lecture, I'll do it from the point of view of quantum groups. OK? Thank you. Okay.
Questions? Maybe we can ask the best questions and all if someone wants to ask.
Yeah, we